Okay, so the next part of this question is that we want to prove that f is, this is the second part of question number 4, exercise number 4, where we want to prove that f is onto, right? So let me make a so basically the question was that basically f was a function from R into the set x belonging to R such that -1 is less than x less than 1, and that is defined by f of x is equal to x over 1 plus absolute value of x, and you want to show that f is onto. This is exercise number 4, right? So in order to show that that basically f is onto, so what you can do is that, so to show that f is onto, what you want to do is that you want to show that basically that this is the case, that basically all of these elements in the codomain of the function are basically the images of some element in the domain of the function, meaning that something like this where an element is basically left alone is not the case. So now what I can do in order to show that is that I need to basically so over here, basically the codomain of my function is this set over here, right? So I'm going to assume that, for example, y is an arbitrary element belonging to this set. So basically let us assume that for example some element like y is an arbitrary element of the set of basically, let's say, of the range of f, It's an arbitrary element of the range of f, meaning that since it's an arbitrary element of the range of f, so then you can say that y is equal to f of x is equal to basically the x over 1 plus absolute value of x. Now what this means is that now we need to find x in terms of y. So this means that basically y is equal to x over 1 plus absolute value of x. Now here basically you will have two cases over here. It doesn't help me to, meaning that I could write y times, for example, 1 plus absolute value of x is equal to x, and then y plus y times absolute value of x is equal to x, and then I couldn't do anything here because over here I have I have absolute value of x, I have x over here, so I cannot take them out, so it's just not possible to do anything in that basically in that state. I have to consider two different cases. So then there will be two cases, and basically case one is that basically x is greater than or equal to 0, where basically y becomes basically x over 1 plus x, and case 2 is that x is less than 0, where basically y becomes x over 1 minus x, right? And that's based on the fact that basically f of x is equal to the absolute value of x is equal to x and negative x, depending on here basically x is greater than or equal to 0, and here x is less than 0. So that's basically the absolute value function. And then based on that you can write these equations. Now in case 1 you have basically x is greater than or equal to 0, and basically y is equal to x over 1 plus x. This implies that basically y times 1 plus x is equal to x, which means that y plus xy is equal to x. This means that y is equal to x minus xy. This means that y is equal to x times 1 minus y. This means that x is equal to y over 1 minus y, right? So what this means is that now you need to figure out whether for every element basically belonging to this set, that for every element belonging to this set there is some element basically in the domain of the function that maps to that element. So, and as you can see here basically the problem with this is that basically here you can see that 1 minus y cannot be equal to 0, which means that negative y is not equal to negative 1, which means that y is not equal to 1, right? So y is not equal to 1, which is not a problem. Because in this set basically x is not supposed to be equal to 1, it's just less than 1, so it's not a problem there. And for all numbers between negative 1 and 1, you can actually test, meaning that now sometimes it's not easy to see that in algebra, but suppose that for example for y is equal to 0.5, right? So suppose that there is some element over here 0.5 or 1/2, and you want to know if there is some element in this set that maps to that element. So you set y is equal to 1/2 to see whether you can find some x for that, right? Which means that if I set y is equal to 1/2, I will get basically 1/2 over basically 1 minus 1/2 is equal to x. So x is then x would be equal to basically 1 minus 1/2 is equal to negative 1/2. So 1/2 over negative 1/2 is equal to x, and therefore x is equal to negative 1, which belongs to the set of real numbers. and this is important, it's important that x can be found here, which is the set of real numbers. Whatever sort of number that you try in this manner, you will end up with some number that can be found in the set of real numbers, because this is the set of real numbers. And based on that, you can conclude that for every y belonging to this set, which is this set over here, which is the codomain of f, there is some element in the domain of f that maps to that element, right? And that's basically the meaning of the concept of being onto, right? So you can say that, you can basically conclude that therefore for x is greater than or equal to 0, for every y belonging to this set -1 to 1, which is the codomain of the function, there exists some basically x is equal to y over 1 minus y, such that f of basically y over 1 minus y is equal to, now you see that f of x was equal to x over 1 plus absolute value of x, right? And here we are saying that x is greater than or equal to 0. So that means that f of y over 1 minus y is just simply in f, wherever you see an x, you have to substitute it with this expression. So that means that this is equal to simply, I'll write it over here because there is no enough space over there. So f of y over 1 minus y would be equal to basically in f, wherever you see an x, substituted with this expression. That means that this is y over 1 minus y, and then over here you have 1 plus the absolute value of x. Now this is, since x is greater than or equal to 0, that means that you have positive x over here. So that means that the positive of this expression, which is y over 1 minus y, which is the same thing as y over 1 minus y, and then 1 plus this is equal to basically 1 minus y, and then 1 minus y plus y, right? And then you can cancel these out, and then you have y over 1, which is equal to y. So this is equal to y. So as you can see, everything works out okay, and you have no problem there. And so you can say that for x is greater than or equal to 0, for every y belonging to the codomain of the function, there exists some x equal to this, such that f of that value is equal to y. That means that all of your y's are essentially covered, from which you can conclude that for all x's greater than or equal to 0, basically f is onto, right? F is onto. And it's important to basically, when you write something, if I just simply write that, for example, therefore f is onto, it's just not right to write it that way, because it's just not, it wouldn't be a correct statement. A correct statement is the kind of statement that helps people understand something without ambiguity. And over here, what I'm saying is that for all x's greater than or equal to 0, f is onto. which is a correct statement, there is no problem with that. And basically x is less than 0, since I haven't checked that, I don't know, so I'm not making any statements about that, right? I'm just making a statement about the x is greater than or equal to 0, and I have checked that, and I know that what I'm saying is true, right? So now case 2 would be basically x is less than 0, y is equal to x over 1 minus x. So you can say that case 2, now it's very easy to get lost in the middle of an exercise like this, because this is something, this type of exercise is a little bit lengthy, and there is a whole lot of things to remember, right? And therefore for the same reason, it's absolutely important to write the important things, to write them down, because if you don't write them down, you will forget them, and then if you forget them in the middle of the exercise, you will simply get lost. But the way that I'm writing this down, there is no way for me to get lost, because now I know that, for example, now I know that I have to go back and examine case number 2. And for case number 2, I have already written down all the necessary information. So then there is no way for me to get lost or anything. So, but suppose that, for example, if I just write that case 2, x is less than 0, and if I don't write this part of the information, then I don't know what to take for the value of y, and so it would, I wouldn't simply be able to solve the problem, right? So y is equal to x over 1 minus x. So over here x is less than 0, and basically y is equal to x over 1 minus x. And we know that basically so basically what you want to do here is that you want to calculate x here, right, in order to see whether your function is onto or not. So what that means is that then I can cross multiply. I'll get y times 1 minus x is equal to x, which means that basically y minus xy is equal to x, which means that basically y is equal to x plus xy. Y is equal to x plus xy, which means that basically y is equal to x times 1 plus y, and that basically means that basically x is equal to y over 1 plus y. Now basically you can see that 1 plus y is not supposed to be equal to 0, which means that y is not supposed to be equal to negative 1, which is not a problem, because y is and you need to, of course, if you understand your notation, you can always check whether something is a problem or not. As you can see, for example, over here I'm saying that y is not supposed to be equal to negative 1, and then I know where to go and check. I know that I have to check over here, because I have basically I have assumed that y is an arbitrary element of the range of the function, and this is the range of the function, right? So that's basically the importance of understanding your own notation. So since basically x over here is greater than negative 1, and it's not equal to negative 1, therefore it's not a problem that it's not a problem that y is not equal to negative 1. So I just write it over here, but it's just not a problem. Now again, you need to, based on this, so over here x is equal to y over 1 plus y, where y is not equal to negative 1, right? So what that means is that then for every y belonging to that set, for every y belonging to that set, to basically for every y belonging to basically to this set from negative 1 to 1, there has to exist some element in the domain of the function that basically maps to this element here. And what that means is that in this expression you can set the value of y to any number between negative 1 and 1, not equal to negative 1 or 1, and then the corresponding value of x is supposed to exist in the set of real numbers, because this refers to the set of real numbers, of course, to the domain of the function. And that is of course the case. Whatever you do over here, you will get some x belonging to the set of real numbers. And of course y is equal to negative 1 is not allowed, which is not a problem, because you're not trying that number anyway. You don't really need it over there. And so over here you can conclude that therefore for every y belonging to the set negative 1 comma 1, basically the codomain of the function, there exists and some, or you can say some x equal to basically y over 1 plus y, y not equal to negative 1, such that f of basically this element or this expression y over 1 plus y is equal to, and you know that f of x is equal to x over 1 plus absolute value of x. You know that f of x is equal to x over 1 plus absolute value of x, right? And here we are saying that basically x is less than 0, right? So we need to take that into consideration as well, right? So now f of x is equal to this is the definition of f of x is this thing over here. And so in the definition of x, wherever you see an x, you have to substitute it with this expression. And what that means is that so then based on these two pieces of information, you can say that f of y over 1 plus y is equal to basically in f you can write y over 1 plus y, and then 1, and you can we already saw that over here that x is less than 0. That means that when x is equal to 0, of course the absolute value of x is equal to negative x. So then I have to write this as 1 minus minus of x, which is the negative of this thing over here. So the negative of y over 1 plus y, right? So that is equal to basically y over 1 plus y, and take the LCM over here as 1 plus y, and then this becomes 1 plus y minus y, and then these two you can cancel out, these two you can cancel out, you'll be left with y, right? So this is equal to y, such that f of y over 1 plus y is equal to y. That means that for every y that you find in this set, there is some x equal to this that and this belongs to the set of real numbers, by the way. there is some x equal to y over 1 plus y belonging to the set of real numbers such that f of y over 1 plus y is equal to y. And as a result of that, for all the negative x's, basically f is onto, meaning that all of these, all of when x is equal to 0, when x is less than 0, then all of the corresponding y's are basically are images of some elements in the domain of the function, right? So therefore you can say that for all x's less than 0, basically f is onto. F is onto. And therefore now we have shown over here that for all x's greater than or equal to 0, f is onto. And over here we have shown that for all x's less than 0, f is onto. And therefore you can say that f is onto for all x belonging to the set of real numbers, right? So that is basically how you would solve this problem. Okay, that was question number 4. And as you can see, these problems take a little bit of time, but that's not a problem. I mean, when you want to do something, you have to do it. There is no other way. Okay, so now suppose that you want to show that this is question number 5, of course, exercise number 5. And suppose that you want to show that basically the function, show that f as a function from R to R, given by f of x is equal to x cubed is injective. Of course, you know that basically injective means 1, 1. It means 1, 1. And basically 1, 1 means that you want to show that basically that your function looks like this and not something like this, where, for example, f of 1 is equal to a, f of 2 is also equal to a, f of 1 has to be a, f of 2 has to be b, f of 3 has to be c, and so on and so forth. So that is the meaning of injective. Now, basically the algebraic condition that we use for this type of situation, as you know, is basically for every x1 and x2 belonging to R, basically the domain of this function, then f of x1 is equal to f of x2. That implies that basically x1 is equal to x2, right? If this condition is fulfilled, then that means that the function is injective. And basically, it's of course always a good idea to understand your toolkit functions. There are about 10, 12, or not more than that, 10, 12 functions that you can call toolkit functions. I think this term has been used in a book in one of the mathematics books in OpenStax, related to some OpenStax books. And these are basically, I mean, simply said, it's those basically famous functions. For example, f of x is equal to x, f of x is equal to x squared, f of x is equal to absolute value of x, and the types of functions that you need to know. And then basically, if you know a little bit about transformations on these functions, then basically you already know how to then your mind essentially becomes a graphing calculator. Then you can draw all of these functions in your mind. For example, if you give me some function plus some function, for example, like f of x is equal to, for example, x squared plus 7, and for example 3 times x squared plus 7. Of course, you can have this function graphed on a graphing calculator, but then I mean, right now that I'm talking to you, I have a mental image of what this function would look like based on what I know from, for example, the function f of x is equal to x squared. I know what this function looks like. It's a function like this, right? Goes through the origin, and then it's in this manner. Now, of course, you can tell that when I multiply a 3 by this is essentially the output of your function, right? So when I multiply a 3 by the output of the function, that means that the function is going to be stretched vertically, meaning that all of these points will be stretched vertically, meaning that, for example, instead of getting, for example, 1, 0, you will get 1, 3. And so your function essentially is stretched vertically, something like this. It becomes essentially a little bit narrower. And you can see that over here. So for example, if I say that f of x is equal to x squared, you can see that this is the f of x is equal to x squared. Now, if I say that f of, man, you can do the same thing on the same function, or you can say that g of x, for example, g of x is equal to, for example, 3 times x squared. You can see that the function, since the function is stretched vertically, it seems as if the function has become horizontally, it's been kind of compressed, but that's actually not the case. The case is that it's exactly been stretched vertically, so it seems that it's been compressed in a horizontal way. So that's basically that. So then you will be able to, for example, see in this your mind, and of course, since you're adding a 7 to the output of your function, then of course you can imagine that the whole function will be shifted up vertically by 7 units, meaning that the function will be somewhere over here, starting from 0, 7. This point would be 0, 7, right? And so basically, then if you give me any function like this, any function that is not too complicated, for example, if you give me some function like, I could even do rational functions. There is also ways to do that. But then if it gets too complicated, of course, then you need to at least do a little bit of algebra in order to figure out the roots of the equations and so on and so forth. But it's essentially possible for almost all functions. And so basically then you will be able to see all of these functions in your mind. And well, I don't really know how that works in case of other people. I'm not an algebra person. Some people must be or might be algebra people, meaning that if you give them an equation, they can figure out all the possible different cases based on the equation that you give them. For example, in physics, for example, there are some people are so good at algebra that if you give them, for example, the relationship between initial velocity and acceleration and initial, for example, position and so on and so forth, That would be, for example, you essentially give them some x of f, for example, is equal to x of 0, for example, plus v bar times t, right? So this is some equation, some relationship between final position, initial position, average velocity, and time. This is in kinematics in physics, for example. But you can think of this as some algebraic expression or some algebraic equation. Then these people can, what they can do, they can tell you, they can give you all different types of different scenarios based on the equation that you give them, meaning that they give that they tell you that if for example no time has gone by, meaning that if t is equal to 0, then your final position is equal to your initial position because you have not moved, right? You have not moved because t is equal to 0. Now this is something simple, of course you can figure that out. Or for example, they can tell you that the difference between your final position and your initial position would depend on how much time is going by and how fast, for example, position is being changed, or how high basically the value of velocity is, or something like that. So they can figure out that the higher your velocity, the sooner you're going to get more away and farther away from your initial position. And of course, the more time goes by, the more you are going to get farther and farther away your initial position, and so on and so forth. And they can figure all of these different. And of course, this is just some simple equation, but there are some more complicated equations in physics. They can figure all of these things out only based on algebra. I call them algebra people. I'm not an algebra person. But of course, that also depends on how much you work with algebra. The more that you work with algebra, the more you will get proficient with algebra, and essentially you will eventually be able to do that as well. But I'm really not there yet, so I have to do a lot of thinking when I want to make sense of some algebraic expression. So that's that. But I don't really know why. Probably because I have been working, or whatever the reason is, I don't really know. I'm a graph person, meaning that any graph that you give me, I can give you basically all kinds of, I can figure out what sort of situation that graph is going to describe. And just by taking a look at the graph for a couple of seconds, I can tell you everything about that particular situation. And well, over the years, I have done a couple of courses on, I used to do courses on Udemy. I have done a couple of courses on how to manipulate functions and that sort of thing. So I can tell you, for example, how a function basically looks like on a coordinate system and things like that, which is of course a very good, basically a very good skill that you could have, because then you could, I mean, for example, right now I can tell you that for example this function is 1, 1, right? Based on the graph of the function, I can tell you that the function is 1, 1. So basically this function would look like something like this. The function would look like something like this. It's basically a function like this. It is a function like this, right? It is a function like this, and this is the function of, this is the graph of the function f of x is equal to x cubed. And as you can see, it is just like a straight line, except that at some points basically the slope is changing a little bit. Otherwise it's just like a straight line, just like, for example, the function f of x is equal to x, something like this, and the function is 1 1, right? So this way, if you basically make some mistake in algebra, meaning that, suppose that using algebra you figure out that for example your function is not 1 1, but then based on the graph you already know that the function is 1 1, so you must have made a mistake in algebra, then you can go back and take care of the problem. So that is basically that. Now, in order to show that this function is injective, this is the condition, then that basically means that I can say that if I assume that f of x1 is equal to f of x2, then basically x1 cube is equal to x2 cube, right? x1 cube is equal to x2 cube, and these are basically important things in algebra, of course, which you need to know. So now you want to know what is the relationship between x1 and x2. So whenever you have x1 cube is equal to x2 cube, so basically you know that always the cube root of taking the cube root of some expression like this, when you have x1 cube, and take the cube root of that in order to come up with some expression for x1, and taking the cube root of x2 cube in order to basically come up with some expression for x2. So the cube root of x1 cube is going to be equal to x1 at all times, meaning that if x1 is a negative number, it's the cube root of x1 cube is going to be equal to a negative number. If x1 is equal to 0, then the cube root of x1 cube is going to be equal to 0. If x1 cube is equal to is a positive number, then the cube root of x1 cube is going to be a positive number, meaning that, suppose that you have, for example, x1 is equal to negative 2, right? Is equal to negative 2. So then you have x1 cube is equal to basically negative 8, right? Because negative 2 times negative 2 is positive 4. Positive 4 times negative 2 is negative 8. And you know that the cube root of negative 8, the cube root of negative 8 is equal to negative 2. Moreover, if you have x1 is equal to positive 2, then x1 cube is equal to positive 8, and the cube root of x1 cube is equal to basically positive 2, right? And of course, if your x1 is equal to 0, then 0 cube is equal to 0, and then the cube root of 0 is basically equal to 0. So at all times you can write the cube root of x1 cube as x1, no matter whether x1 is negative or positive or 0. So that's simple. And this is equal to x2. So x1 is equal to x2, right? And but then of course you need to be careful, and hopefully we will get into some example where we need to do some algebra on a square root function. In that case, I'll tell you a little bit about the square root function is a little bit tricky, and that's where most people make mistakes. So now basically it's essentially f of x1 is equal to f of x2. This implies that x1 is equal to x2, and therefore basically f is 1 1. Let me see what the solution here is. It doesn't make much sense. Number 5. Well, they have actually solved the problem in a way that doesn't make much sense. So the way that they have solved the problem is as follows. What they have done, of course, you can simply use algebra. So here you can say that therefore basically f is 1 1, right? What they have done is that for whatever reason, which is of course an interesting way of solving the problem, but I don't really know why. I don't really see why that's necessary. So we have f is a function from R to R as f of x is equal to x cubed. Now, to show that basically f is 1 1, basically you suppose that f of x is equal to f of y, right? Where basically x and y belong to R. Some x and y from the domain of the function. And now we need to show that basically x is equal to y, meaning that this condition has to be true. So since f of x is equal to f of y, that implies that basically x cubed is equal to y cubed. Now suppose that here this is how they have solved the problem. They have written suppose that x is not equal to y, and if that is the case, their cubes will not be equal. Which is a contradiction to, let's call this 1 for example, which is a contradiction to 1. And therefore you can conclude that x is equal to y. So here we are assuming that x is not equal to y, and as a result of that, some contradiction arises. So since contradiction is not supposed to exist, then we can conclude that basically whatever it is that we assumed was true is not true, meaning that we said that it's true that x is not equal to y. Then you can conclude that it's not true that x is not equal to y. That means that x is equal to y, and that is basically your conclusion. And then hence f is injective, or 1 1. Now I wrote this down because this is actually an interesting way of solving the problem. So I mean, you can actually learn this type of proving things and use it in the case of other problems. So that's why I wrote it down. Otherwise, I would simply use algebra in this case. It's not really necessary to do this, but in and of itself, the the method that they have used in order to prove this is actually interesting. So that was question number 5. Now question number 6, we have, I need to take care of a couple of things. Okay, so the next question that we have is the type of question that I don't like, because it takes a lot of thinking for most of the time. Not a good reason at all, but let's go through the problem. So you want to give exam, and I need some more space, of course. You basically want to give examples of basically, this is question number 6, of two functions f as a function from n to z, and g as a function from z to z, such that basically GOF is injective. GOF is injective, but G is not injective. It's actually not that bad a question. But G is not injective. So basically what that means is that you have a function f from the set of natural numbers to the set of integers. G is a function from the set of integers to the set of integers, right? And you want to give examples of two functions. You want to actually find basically two definitions for f and g in such a way that GOF is injective, but G is not injective. Meaning that GOF would be, let's say that GOF of x is the same thing as G of f of x, right? So that means that basically f of x, whatever that is, suppose that you have the set of natural numbers here, and you have the set of integers here, and f is basically some function that goes from natural numbers to integers, something like this. And then if you have x over here, you have f of x over here, right? And then basically g is a function that goes from z to z, which you can imagine that, for example, some situation like this, where basically you go from g is a function that you give f of x to g, and then it gives you g of f of x, which is what you get here, and this is z as well. So what that means is that basically g of f of x, or GOF, is actually a function that goes from this set basically directly to this set over here. This is GOF. Now you want to specify two functions. You want to specify these two functions f and g in such a way that basically GOF is injective, meaning that this function is 1, 1, but g is not 1, 1. But g is not 1, 1, right? So that's basically the situation here. Now I'm going to take a look at the solution here, because I don't like to think about these types of problems. And as a hint, you can consider f of x is equal to f of x is equal to basically x, and g of x is equal to the absolute value of x. So if f of x is equal to x, that means that this function is 1, 1, but this function, of course, is not 1, 1, right? And so what happens is that f basically takes every x to some f of x over here, and f of x is equal to x, and the function, of course, is 1, 1, but then this is not 1, 1. This part over here is not 1, 1 because you're dealing with some function like this. This is the absolute value of x. This is not 1, 1, of course. And the reason for that is that, for example, if you take this output and map it to you would get two inputs with different values for the same output, meaning that the function is not 1, 1. Now suppose that I give basically 1 to this function, I'll get a 1 over here, and then I'll get a 1 over here. Give it 2, you will get a 2 over here, and I'll get a 2 over here. Give it 3, you will get a 3 over here and a 3 over here, and so on and so forth, all the way up to infinity. The function is, of course, going to be 1, 1, meaning that g of f is 1, 1, but g is not 1, 1. So that's basically the solution, I suppose, right? There's nothing mysterious about this question. Right? So I could actually write down the logical basically argument, but it's not really important. As long as you understand that basically the absolute value function is not an injective function, and this identity function is actually it's a function like this. So it's actually a 1, 1 function, and when you put these two functions together, meaning that when you get the output of this function to the input of this function, then you will have basically the output is going to be these positive numbers, meaning that you're mapping all of these natural numbers to these natural numbers, and it so happens that 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3, all the way up to infinity. And so, of course, g of f becomes 1, 1. There is no problem with g of f, but g is not 1, 1. And of course, f is actually 1, 1. So, you want to keep this in the back of your mind. Of course, you might be actually someday be able to use this somewhere, but this is essentially the proof, or not the proof, but the solution. And that's basically the end of the story. Now I'm going to end this video here. In the next video, we will continue with these exercises. Thank you.